the relation of exponential to Poisson. Both are, as I mentioned, two faces of the same coin, Poisson distribution. Okay, exponential is continuous and our Poisson is discrete. I mentioned in the last video also, I'll mention it again. Two faces of same coin. What is the commonality? What are they measuring, and what makes that so common? Okay, so Poisson distribution models, what does it model? It models the number of events occurring in a fixed interval. Okay, it models the number of events occurring in a fixed interval, given that the rate of events is constant. The average rate of events is constant, and that is given by lambda. Okay, for example, number of calls a customer care center will receive in an hour. Okay, so this use case can be modeled using Poisson distribution. So this is our Poisson case. Poisson, what does it model? It models the number of events occurring in a fixed time interval. What is given? A constant rate at which the constant average rate, this is called lambda, denoted by lambda. Okay, and what does Poisson exponential distribution? So here you see that is counting number of events. So this is some discrete, how many events will happen, 1 2 3 4. So this is what it makes it discrete. And what is exponential measuring? Exponential is measuring the continuous time that will pass between these two events. So that's what makes it continuous. So this will measure the time interval between two successive events. I'll just write 2 events. Okay, so that's why it is counting the number of events. Say for example, there are, I'll write this is like some time t, hour, whatever time, and say on average rate of events is 1 2 3 4, whatever. Okay, say Poisson counts, okay, what is the probability of how many number of events happening in this fixed time t. So exponential distribution will measure the time between them. So if you see, this count is discrete and the time, this is continuous. So exponential will measure the time between these two events. Okay, that's the relation between these two. Okay, and now let's understand how they are related mathematically also. So I hope the intuition of this the intuition is clear. Okay, so shall we see some graphs? Okay, let me show you the wiki pages of this. So let's see the Poisson distribution wiki. I go to wiki for all this. So let's see wiki. So it is the documentation is very good. Okay, there, but only the language is a bit tricky. So that's the only thing there. But the graphs are very good. They are very self-explanatory. If you see here, Poisson distribution. So here it's given lambda equal to 1, lambda equal to 4, lambda equal to 10, and the Poisson distribution plots are given here. This is the PDF of Poisson distribution. Okay, and these are the discrete points, how many number of events will happen and what will be the probability for each lambda. So the graphs are very well drawn. Similarly, this is the CDF here, and the other statistical properties which are very good. Okay, similarly we can search for exponential also, exponential distribution, and here you see this is the exponential curve for each lambda, the constant rate. So again, constant, right? This is the waiting time between the events that we saw there, right, on the Poisson curve. This will give us the waiting time. Okay, so refer this. This is very good. All the PDF and the CDF also. This is 1 minus exponential. This is the CDF of it. X less than x, right? So this is both the exponential curve. This is the decreasing exponential. This is the increasing exponential because it is summation. Okay, all this is very good. It's good. Refer this. So now let's come back to the maths and understand that what's the relation and how. Okay, and both the rates are constant. The lambda Poisson is identical to rate parameter. Okay, so the you can say that lambda Poisson is identical to the rate parameter of exponential distribution, lambda exponential. I'll just try to explain. So let's prove it. So let's do the math. I'll go to the next page. So what is the proof? So let's hold the formulate the problem. Okay, so the probability of observing exactly k events in an interval of time length time t is with an average rate lambda, with an average rate of lambda events per unit time. What will be the formula for that? So now we are telling that the average rate of observing events per unit time is lambda. So lambda is average rate of events per unit time, and what is my time interval? So this is the time interval. Okay, length of time interval. So in this, so if this is the average rate lambda and this is my time interval, how many events do we, what is the average rate of events now? So average rate of events would be lambda t. Okay, and we want to observe the number of okay, observing. So we want to, so number of events observed is equal to k. So exactly k. So what will be the from the PDF of lambda distribution? We know the PDF. So probability of seeing k events in the same interval would be, so instead of lambda, now this is the average rate, so this will become lambda t. This will become lambda t to the power k, and this will be e to the power minus lambda t. So the wherever lambda is there, we replace it with lambda t now. So this is because we have made lambda as average rate per unit time, and then we are multiplying it with the time just to get the show the maths. Okay, by k factorial. So this is your Poisson. So now we are seeing it from the Poisson perspective. Okay, now even that waiting time until next event is greater than t. So we saw an event, and what is the probability that the waiting time is greater than t? Okay, what will be that event? So if we have observed one event, and then we have waited, and we want to find out that the waiting time is greater than some time t, means no event has happened in this time interval, right? So for example, I have seen an interval at some time x equal to t0. So this event happened. Okay, and then now the next event, we want to find out that whether in this time x greater than t time, okay, here x greater than t, whether any event happened in this or not. Okay, so how do we find out if this number of events observed in this event is 0, in this time period is 0? So if k is equal to 0 means I have not observed any event in this time, in this waiting time. right? So this is what will give me the waiting time, so that I can compare the waiting time with the exponential distribution. So what does this say? So if we have not observed any event, okay, the event of waiting time, okay, the event that waiting time, okay, until the same thing what I have discussed, I'll try and write until next event is greater than t is same as observing k is equal to 0, sorry, I'll write it, k is equal to 0 events in that interval. I have waited and no interval happened, no event happened. Whatever was the average rate, even then no event happened, then we can say that the waiting time was greater than t. So this is the main intuition. Okay, now let's check. So what will be the probability of that? Using the probability p of x equal to 0, because here k is 0, is will be, and what was the formula? Lambda t to the power 0 e to the power minus lambda t by wherever k is there, replace k with 0. This k becomes 0, this becomes 0. So this will become 0 factorial. This k becomes 0, this k becomes 0. Okay. So this will become lambda t to anything to the power 0 is 1, 0 factorial is 1, and this will become e to the power minus lambda t. So this will be e to the power minus lambda t. Does it look similar to exponential now? Let's solve the exponential side also. Let's move to the next page and solve the same problem using exponential. So what will be the exponential formulation? How will you formulate that using exponential? Now let's consider the exponential side and the waiting time. Okay, exponential. So it models the waiting time between two events. It models the waiting time. Okay. Until next event. So what is the probability? Same thing. The event that waiting time t is greater than, sorry, event that the waiting time x is greater than t is similar to observing 0 events. Similarly, we know what is the, from the CDF, that probability of, this is CDF, of x greater than x is equal to e to the power minus lambda x. We know this, we have seen this earlier. Okay. So now what will be the probability that waiting time is greater than some time t, this x will become equal to t. So this will become probability of x greater than t is equal to e to the power minus lambda t. So you see this and you see this. So this both give e to the power minus lambda t here and e to the power minus lambda t here. So this proves that Poisson and exponential distribution are just two faces of the same coin when no event happens in the given time. Then this is, both will give the similar thing. I hope this is clear.